the port of Bunbury, 115 miles south of Perth, Western Australia. You are approaching the titanium oxide manufacturing plant of Laporte Titanium Australia Limited.
Good morning, sir. Who do you want to see, please?
Good morning. I have an appointment with Mr. Gosling.
Right through on the left, on that low building.
I see. Thank you very much. Well, Mr. Gosling, I hope you don't mind me dropping in on you at short notice like this.
Not at all, Mr. Calvert. It's always a pleasure to have a visitor from the eastern states. Would you like me to arrange for somebody to show you around the plant?
Yes, I would. Thank you. By the way, is that a photograph of the plant?
No, in fact, it's an artist's impression of the plant, which was done before construction started. Here's Mr. Longbottom, our works chemist. Peter, Mr. Calvert of the Sydney Paint Company.
Mr. Calvert?
Peter, could you arrange to take Mr. Calvert round the plant and laboratories, please?
Sure, be a pleasure. Care to come this way and I'll fix you up with a hat and coat.
The Laporte titanium plant at Bunbury was officially opened in November 1963, and the first pigment was made in January of the following year. Construction had been a most complex task. The site had been cleared in March 1962, and the construction workforce rapidly built up to a peak of 800 men on site. Most of the equipment was supplied by Western Australian industry, although some came from the eastern states and small quantities from Germany, Switzerland and the USA. The number and variety of items installed for the titanium dioxide process were quite remarkable. 400 electric motors ranging up to 250 horsepower, 150 pumps, over 200 tanks of various sizes up to 16,000 gallons, 16 miles of pipework and 60 miles of electric cable were laid down. In terms of money, the project represented a $9 million investment for Laporte Industries Limited. Of the total available site area of 150 acres, the present plant covers approximately 20, leaving ample space for expansion. At the moment, the plant is producing 10,000 tons per annum of titanium oxide in various grades with a total labor force of 220 people. The imported sulfur seen here is loaded into the sulfur melter for the manufacture of sulfuric acid. This is one of two basic commodities necessary for the production of titanium dioxide by the sulfate route. The sulfuric acid plant is a conventional contact process capable of producing in excess of 120 tons per day of 100% H2SO4. 4 tons of acid are needed to produce 1 ton of titanium dioxide. Being a standard and well-proved process throughout the world, it is almost fully automated, and a plant this size can be controlled by one trained operator. The basic raw material is locally mined ilmenite, which comes onto the site in road trucks. It is pneumatically conveyed from the truck into a storage bin and then to a steel ball mill for grinding. This particular ilmenite contains nearly 55% titanium dioxide, the remainder being very largely iron, with small percentages of siliceous matter, aluminium, manganese, chromium, etc. The ground ilmenite is mixed with concentrated sulfuric acid and is pumped into a sulfation machine which operates continuously. The heat of reaction is high enough to drive off surplus water, so that the resulting sulfates of titanium and iron are in the form of a brown, friable cake at this stage. The essence of a consistent product is rigid control at each stage of production. This control room is typical of a number throughout the plant. The brown friable cake drops from the sulfation machine into tanks where it is dissolved in dilute sulfuric acid. The acid-insoluble material gives the liquor a dirty brown appearance. The remainder of this section is devoted to the clarification of the dirty liquor by flocculation and filtration. Also, by cooling the liquor down, some 60% of the iron associated with the titanium sulfate is crystallized as ferrous sulfate, or copperas, and is removed in this centrifuge as a waste product. The processes we have seen, plus filtration and evaporation, result in this clean, black, viscous liquor ready for precipitation of titanium. This precipitation of the titanium hydrate by hydrolysis is automatically controlled. The processed liquor changes color on hydrolysis from the black liquor seen so far to the familiar white suspension associated with titanium oxide. The titanium hydrate from the hydrolyzers is still far from being a pigment. Filtration is used to remove the large quantities of iron and other soluble impurities which are still associated with the hydrate. The first stage of filtration is shown in operation here. Rotary vacuum filters continue the cleaning up process until the concentration of iron impurity, for instance, has to be measured in terms of parts per million on the titanium dioxide. Certain alkaline treatment chemicals must be added to the pulp prior to feeding into the calciner to control the texture and particle growth of the titanium dioxide, which takes place during its approximate 18-hour passage through the kiln. Temperatures of up to 1,000 degrees centigrade are attained in the kiln, and it is the control of calcination conditions which determine whether the pigment will be produced in an anatase or rutile crystal form. When the rutile form is being produced, samples are taken regularly from the calciner cooler and checked for complete conversion to rutile by an X-ray technique developed in Laporte's physics laboratory. After the pigment is milled, a small percentage of the production is bagged at this point for marketing as a straight anatase or rutile pigment.
Well, this used to be an end of the process. But as you know, in the early 1950s, it was found that the dispersibility of some optical properties of the pigment could be very greatly improved by the precipitation of some metallic oxides on the surface of the pigment particles. Nowadays, of course, these surface-treated grades constitute the vast majority of the titanium dioxide pigments that are available. This surface treatment process is virtually another plant, forming a continuation of the one we have just seen. Instead of going into bags, the calcined and ground pigment is dispersed in water using both chemical and mechanical dispersing techniques. This dispersed slurry is then classified in order to remove all particles of pigment greater than 4 microns in size. The slurry of fine material passes forward to the treatment tanks where the various metal hydroxides are precipitated by neutralization. Then follows washing, drying, and fluid energy grinding in micronizers. Bagging and metal contamination checking complete the process. Well, that's the basic process, and I think you'll agree that it's quite a complex one. So that we can produce a consistent quality, careful plant and laboratory control of each unit operation is absolutely essential. Although some operations are carried out batch-wise, the main flow from the ilmenite through to the packed pigment is a continuous one. This particular section of the laboratory is occupied by shift chemists who are checking process samples taken at regular intervals throughout the plant from ilmenite to final pigment. Day staff cover such things as raw materials, services, and development work, as well as the chemical analysis of the pigment. This part of the laboratory you'll probably be most interested in. This is where we make a final evaluation of the pigment for its end-use properties before its dispatch. A representative sample of every 5 pounds of pigment packed is taken, and this constitutes a batch.
Just what are the tests that you do on this sample?
Well, our testing schedule is indicated on this board. The color of the pins is indicating the stage which the tests have reached. Not every batch can be checked as completely as this, of course, but all batches are checked for basic properties such as dispersibility, pH, percentage rutile, and color.
Color. How do you measure your color?
We use a color master. Let's go and take a look at it. This has proved to be the best instrument for our type of work. Using a dry plug of pigment, the brightness and yellow tone are examined. Carbon black undertone, which is dependent on particle size, is an important factor in overall color assessment. The color of paint panels prepared with various media are measured in the same way.
This is an interesting mixer.
Yes, this is one example of several techniques that we use to evaluate the ease of dispersibility of a pigment. As you can see, variables such as speed and temperature are standardized. A Hegman reading is taken. The viscosity of the pigment is adjusted at a standard temperature before spinning a film. After 24 hours, the gloss of the spun film is measured. Other laboratory-made and conventional milling techniques are also used to determine the ease of dispersion.
You seem to have covered your oil-type dispersions very well. How do you check your latex dispersions?
Look, there's one being done over here now. By this method, the surface can be examined for any undispersed particles of pigment. Opacity of the pigment is determined by a scattering coefficient technique. This, of course, involves an accurate film thickness measurement. At regular intervals, a full evaluation of all pigment properties is carried out in various types of paint media, such as air drying, stoving, and latex types. These paints are finally put out for exposure. Well, there it is. That should give you an idea of the range of our basic testing. Don't forget, Bob, we're essentially a production unit here in Bunbury. Customer service is handled by our laboratory over in Botany. So if you have any queries, don't hesitate to get in touch with them.
The products of Laporte Titanium Australia Limited are marketed in all Australian states through Laporte Chemicals Australia Proprietary Limited. and overseas through Laporte Industries Limited.